Alright, so let's see how to solve this problem, that is integer multiplication. So essentially we assume that two single digit numbers can be multiplied in constant time. But as the number of digits of a number increases, the time for multiplication will also increase, obviously, right? So how to solve this efficiently? That's what we're going to see now. Alright, so for this problem, the input is going to be like this: a number A and a number B, right? Two numbers, and both of these are n-digit numbers. And let me use the base as 10. Okay, these are two n-digit numbers with base. Okay, let me not fix anything. Let me assume that the base is x. Alright, like when x is equal to 2, this is binary. When x is 10, this is our normal decimal number system, etc. Alright, so A is given in the form of a sequence of n single digit numbers that corresponding to the the least significant digit until the most significant digit. For example, A is given as a n minus 1, a n minus 2 dot dot dot, a2, a1, a0, and B is given as bn minus 1, bn minus 2 dot dot dot, b2, b1, b0. Alright, so this is what A and B, and our task is to find output, find C, which is the product of A and B, or more specifically we want to find C, which is Cn minus 1, C2, C1, C0. So we want to find these coefficients. So note here that these are n-digit numbers, so the product can be either an n-digit number or an n plus 1 digit number. That is why I have n here. This is n minus 1 and this is n. Okay, so how to solve this efficiently? That's the question. So one thing we have seen is the standard textbook algorithm for multiplication. Let's say we have a 4-digit number and another 4-digit number. So how do we multiply? You write one on top of the other. You pick each of the digit from the second number, starting from the least significant one, and you start multiplying that digit with every other digit in the first number, right? So you get all those products. Then you take the second digit of the second number from the right side, again do the same multiplication, then you pick the third one, etc., etc. So in total you will end up in spending a quadratic number of multiplications. So trivial solution, or the standard algorithm or standard multiplication procedure, takes big O of n squared time, right? And the question is, can we somehow improve this bound? Alright, so the answer is yes, and we are going to use the divide and conquer strategy. Alright, so divide and conquer strategy, okay? And we will somehow get a nice recurrence relation and we solve it and we are done. That is how we typically deal with divide and conquer strategy. Alright, so let me just use Tn. Tn is the time for multiplying two n-digit numbers. And my objective is to divide this problem into sub-problems, right? After spending some small amount of time, I kind of want to divide this problem into sub-problems, where each of those sub-problems are also going to be integer multiplications. However, the number of digits in those sub-problems should be lesser than n. And ideally we would like to have something like n over 2, right? So this is where we are going with this. So my first objective is, can I somehow break down this integer multiplication problem between two n-digit numbers into sub-problems, which are again going to be integer multiplications, but on integers of smaller size. Alright, so let's see how to do this. The first thing I want you to notice here is this A or B, I can write like this: a n minus 1 into x raised to n minus 1, right? Then a n minus 2 multiplied by x raised to n minus 2 plus dot 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 a1 x plus a0, right? This is what the actual value of a is, where x is the base. Then the same a I can write like this: a n minus 1 x raised to n minus 1 plus dot 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 until a n over 2 minus 1. I will put a ceiling and multiplied by x raised to n over 2 minus 1, right, plus a Alright, so all I have done here is this: I just took the first, so n over 2 ceiling is, just to take care of the scenario where n is an odd number. So roughly speaking, what I have done is I have separated these integers into two parts, roughly n over 2 integers on the first side, on the left side, and n over 2 integers on the right side. So I have divided this into two parts. And one thing you can see here is all of these terms have something in common, which is nothing but this term, right? This is x to the n over 2. This is supposed to be something like this. Okay. X to the n over 2, there is a ceiling, is common to all these terms. So what I'm going to do is I'll just remove this ceiling. It looks pretty ugly, but you got the point. Basically, I want to just deal with the scenario where this is n is an odd or even. Okay, so let's assume that n is an even for now. Okay, so I'll take this term outside from all of these terms. Then how this will look like is x to the n over 2 multiplied by a n minus 1 x to the n minus 1 minus n over 2, that is n over 2 minus 1 dot dot dot. The last term is going to be a n over 2 plus this is a n over 2 minus 1 dot dot dot. Okay, so at this point I want you to have a careful look at this. This is a can be written as x to the n over 2 multiplied by, this is a n minus 1, a n minus 2, etc. up to a n over 2. So this is essentially a number which has at most n over 2 digits. Okay, so based on ceiling and floor, it may have n over 2 plus 1 digits. So roughly n over 2 digits. And let me call it as a1. And similarly, this part is clearly an n over 2 digit number. And let me call it as a2. Okay, so what I have done so far is this. I have written A as some A1, which is an n over 2 digit number, multiplied by x raised to n over 2 plus A2. All right, and B, in the same way, I can write as B1 multiplied by n over 2 plus B2. So this much is correct, right? So A, B, A1, A2, B1, B2, where A1, A2, B1, B2 are n over 2 digit numbers. Therefore, what I really want to compute, that is A multiplied by B, I can write as A1 x raised to n over 2 plus A2 multiplied by B1 x raised to n over 2 plus B2. And this, if I expand, what I'm going to get is this A1 B1 x raised to n over 2 plus x raised to n over 2 multiplied by x raised to n over 2, that is x raised to n, plus x raised to n over 2 times A1 B2 plus A2 B1 plus A2 B2. All right. So this is what is the multiplication, which I'm going to call it as C. All right, which I'm going to call it as C. And let's have a closer look here. So one thing is, I want you to notice this multiplication, A1 multiplied by B1. Essentially, this is a multiplication between two numbers where each of them are n over 2 digit numbers. And this is getting multiplied by x raised to n, where x is the base, right? So multiplying with x raised to n, and if you remember, I mean, if you consider x as, let's say, 10, so multiplying by 10 raised to n is what? Simply adding n zeros on the right side. So that multiplication is not very expensive, right? Right? Basically, this is an expensive multiplication. We don't know how to do this. But once we get this, multiplying with x raised to n is not really a big deal. It is simply making some shifts, like shifting the whole thing n positions towards the left side and adding that many zeros. So similarly, this multiplication is easy. We can ignore. However, this is an expensive multiplication, this is an expensive multiplication, and this is an expensive multiplication. So in summary, what we have done now is the multiplication of A and B, multiplication of two n digit numbers, we have reduced to the multiplication of n over 2 digit numbers. And how many of such multiplications? 1, 2, 3, 4. And additionally, you have to do some shifts, because of this, there are some shifts and there are some plus signs in between. So all of these extra things you can do in big O of n time, which means I can write the recurrences, recurrence in this form, T of n. I have reduced to 4 multiplications, where each of those multiplications are between n over 2 digit numbers. And the remaining task can be basically this addition, this addition, this addition, then making these shifts. Everything can be done in linear time. So some constant times n. And let's see how to solve this recurrence. So what you can do is, this you can make as 4 times 4t n over 4 plus c n over 2 plus cn, and if you do this, this will become 4 square plus tn divided by 2 square plus, there is going to be a cn at the end, which is this cn, 4, 2, so that is 2cn. And if you expand this again, what you're going to see is 4 cube t n divided by 2 cube plus 2 square plus 2 plus 1 cn. So in general, this is going to be 4 to the k t n divided by 2 to the k plus 2 to the k minus 1 plus 2 to the k minus 2 dot 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 2 plus 1 multiplied by cn. Alright, so this whole thing, this is a geometric series which can be roughly bounded by big O of, or this can be roughly bounded by 2 to the k. Therefore, the whole thing I can write like this. This is going to be 4 to the k multiplied by t of n divided by 2 to the k plus big O of, there is an n, then 2 to the k. So n multiplied by 2 to the k. And all I know is this quantity, t of 1, all I know is t of 1 can be written as a constant. So when is this quantity going to be 1? That is n over 2 to the k is equal to 1, means n is equal to 2 to the k, or k is equal to log n. So now if I put these things back, 2 to the k is n, so 4 to the k is n square multiplied by t of 1 plus n into 2 to the k is again n, so the whole thing is big O of n square. Alright, so we tried some divide and conquer strategy, but unfortunately no much use. We ended up in getting n square, the same thing as the straightforward algorithm gave us. Alright, so is there anything we can do here to make it better? Alright, that is what we need to figure out. Alright, so unfortunately this recursion is not going to take us anywhere. Alright, so what we understood, or the lesson we learned from this is this: if you break it down into 4 subproblems, where each of them are between, or where each of the subproblem is a multiplication of n over 2-digit numbers, we will not get anything better. But on the other hand, if we can somehow reduce this multiplication, the number of multiplications or the number of subproblems from 4 to 3, then we will suddenly get a different recursion, and hopefully that is going to be better. So now the question is, can we somehow compute these things in less than 4 multiplications? Alright, so this multiplication a1 b1, let's say I will do it. Okay, so let's say a1 b1, I will do the multiplication in one multiplication. Okay, let me also go ahead and compute a2 b2. Now I need to compute a1 b2 and a2 b1, and I don't want to do this in 2 multiplications. Is there a way I can somehow get this quantity with just one additional multiplication? That is a question, and the answer is yes, because of the following equation. So have a look at this. What is a1 plus a2 multiplied by b1 plus b2. If you expand this, what you will see here is this. This is a1 b1 plus a1 b2 plus a2 b1 plus a2 b2. All right, and this is exactly what we want to compute. And this quantity is here and this quantity is here, right? And what you see on the left hand side is you need to add few things, but just one multiplication. Therefore, if you rearrange this formula, what you really want to compute, that is a1 b2 plus a2 b1, can be written as a1 plus a2 multiplied by b1 plus b2 minus a1 b1 minus a2 b2. Okay, so I think the solution is getting pretty clear, right? So what we are going to do is this. First we will multiply a1 b1, one multiplication. Then we will do a2 b2. This is the second multiplication, and this is the and this is the third multiplication we're going to do. That is this multiplication. And once we have these three results, we can easily compute this using some subtractions. Alright, so now let's see how the recursion looks like. So T of n will be, how many multiplications we need? 1, 2, 3. 3 times T of n over 2 plus the remaining all operations can be done in big O of n time, because you are adding two n-digit numbers, that is big O of n, again adding two n-digit numbers, big O of n. You are taking these quantities out, again big O of n. So the whole process can be done in, the whole remaining process can be done in big O of n time. So this will be like this. And if you do the math now, what you're going to get is an equation like this: 3 to the k, n divided by 2 to the k. The same way as before, if you do the expansion, then this will become cn multiplied by 1 plus 3 over 2 plus 3 over 2 square plus dot dot. The last number is going to be 3 over 2 raised to k minus 1, right? And what we need to do is this, we want to make sure that this quantity is 1, therefore n is going to be equal to 2 to the k, or k is equal to log n. So this will look like this: 3 to the log n multiplied by t of 1 plus this whole quantity will become cn times 3 over 2 raised to log n. 3 to the log n is same as n to the log 3, n to the log 3 plus cn. 3 to the log n is same as n to the log 3, and 2 to the log n is same as n to the log 2, which is n. So this n and this n can be cancelled. So the whole thing is going to be big O of n to the log 3, where log 3 is roughly log 3 to the base 2 is roughly 1.559. So therefore the whole thing can be written as 5, 9. Okay, so this is clearly better than n square. And this is called fast integer multiplication. Alright, so this is called alright, and this algorithm has even a name. Okay. Another problem with the same flavor is matrix multiplication. So here we are given two matrices, let's say A and B. A, which is n cross n, and there is an A, n cross n, and there is a matrix B, which is also n cross n, and your objective is to compute a new matrix C, which is also going to be n cross n. So the trivial solution is of n cube, whatever we have learned in the high school. However, there is a nice strategy to apply divide and conquer. So one thing we can do is perhaps we can divide this into 4 submatrices, each of them, and call it as, let's say, A11, A12, A21, A22, and let's say this is B11, B12, B21, B22, and this is C11, C12, C21, C22. Then what I can show is I need to compute these things. So C11 is nothing but A11 multiplied by B11 plus A12 multiplied by B22, right? This, sorry, A12 multiplied by B21. Similarly, C12 is going to be A11 multiplied by B12 plus, right? So this multiplied by A12, 11, B12, A21, B22, then C21 is going to be C21, that is A21 multiplied by B11 plus this, and this, that is A22 multiplied by B21, and finally C22 is A21 multiplied by B12 plus A22 multiplied by B22. Alright, so matrix multiplication, we have reduced it to 8 subproblems, where each of them is again matrix multiplication, but between n over 2 cross n over 2 matrices. And what you can do is you can write the recursion like this, Tn, where Tn is a time for multiplying two matrices of size n cross n and n cross n. So note that n is not the size of input. The size of input here is n square, but I'm just writing the recursion like this. So what I can say is this I can decompose into 8 multiplications between n over 2 cross n over 2 matrices. Then I need to do some additions of these matrices. That's going to cause some big O of n square. And if you solve this recursion, what you're going to get is big O of n cube. Okay, which is nothing interesting, right? Because we already know how to do this in n cube. So this is not anything of use. However, there is a smart algorithm known as Strassen's algorithm, or Strassen matrix multiplication algorithm. This is the name of the guy who came up with this idea. So what he really did is, instead of reducing this thing to 8 subproblems, he managed to bring it to 7. Okay, I'm not going to show the details. You can have a look at the textbook to see how exactly he did it. It is pretty complicated. I mean, I don't know how he came up with this, but it's very easy to verify, but hard to explain the intuition. But anyways, he managed to, you know, reduce one multiplication. So then the recursion suddenly will become Tn is equal to 7, Tn over 2 plus big O of n square. And if you solve this, you will get this as n raised to log of 7 to the base 2. And log 7 to the base 2 is roughly 2.81. So 2.81 is better than 3. So therefore, now we have a faster algorithm for matrix multiplication. So this was n raised to 1.59 and this is n raised to 2.81. Okay, so that is matrix multiplication by Strassen. Okay, so just as a note, this is not the fastest algorithm currently known. There are much more advanced algorithms which takes something like n to the 2.3 roughly. All right. I just want to mention one more example, which is known as the fast Fourier transform. Fast Fourier transform, pretty useful. The simple algorithm or the straightforward algorithm will take big O of n square, and you can apply this divide and conquer strategy to bring it down to big O of n log n. Okay, so these are some of the pretty well-known problems where we can apply divide and conquer and bring down the computational complexity.